sea of polar molecules. So this is, again, like every other talk in this conference, research talk, but I tried to comment a little bit on sort of the role of theory in present and future. I also don't have too much introduction, so let me just introduce the platform, ultracold molecules. Basically, you can think of this as ultracold atoms. The interest is that they'll have dipole moments, which will sort of enrich applications in things like quantum many-body physics, et cetera. But basically, they're, let's say, ultracold atoms. So it's a bit surprising maybe to start talking about the first BEC if you come from this perspective. BECs of atoms have been around since, well, for about 30 years now. And also I'm speaking pretty much 100 years after the birth of quantum statistics. Yeah, maybe the bigger question is why are we so late with molecules? So this is not for lack of trying, right? So people have worked on ultracold molecules since the early 2000s. I put a proposal here by Dave DeMille. I could have also put early work by people who are present. Also on the experimental side, the first gas of ultracold molecules is from 2008, first authored by Kang Quen, who's now here, not in the room, but at Harvard. So now the big question is, how do I get out of this triangle of sadness here? Clearly it's not true. Ultracold molecules are not exactly ultracold atoms. And one of the essential differences is collisional loss, which makes evaporative cooling to a BEC inefficient. So what do we know about these collisional losses? This is, again, the first ultracold molecule, KRB. And this is looking at experimental loss rates. It's a bit stylized. I don't even have a vertical scale. The point is that experimentally observed losses are the markers, and they're reproduced by a very simple model that we call universal loss. So the universal loss model basically says, okay, let's account for long-range interactions, let's say von der Waals interaction between the molecules, and then whenever they come close together, we just assume that they're lost with 100% probability. So this is a huge simplification, and it does reproduce the experiment. But of course, we're then kind of agnostic to what is causing the loss. As long as there's fast loss, you will see rates determined by long-range interactions only. So for KRB, it's not a huge surprise because this molecule is chemically reactive. It can produce K2 and RB2, and then these molecules are just lost. So this then motivated people to build entirely new experiments with non-reactive molecules. These are molecules such as, also bialkalis, RBCS, sodium, potassium, that don't have these reactive collisions. If you would make, let's say, RB2 and cesium-2, that would require more energy, and it cannot happen in an ultracold gas. Then people spent some years building this, and then it turned out that they have loss that is equally fast, is also described by this universal loss model. So there are some sort of chemical reactions of non-reactive molecules, which are only partially understood. So there's this idea that these molecules are sticky, meaning that in principle there are no two-body loss mechanisms, but they can collide and then stick together for a relatively long time, orders of magnitude longer than either ultracold atoms or molecules at higher temperatures. And during this time, they might be susceptible to other loss mechanisms. So one of them might be photoexcitation of collision complexes. So this is a bit of a complicated drawing, but these are the energy levels of two molecules. And when they're close together, the electronically excited states are completely modified. So you can suddenly excite the complex, even though you can't excite the individual molecules. So this actually could explain losses in some molecules. So for example, in Simon Cornish's group in Durham, they did an experiment on rubidium-cesium molecules where they modulated the trap so that on time average, you still have a trapping potential. But then the dark time, the time that the trap is off, is actually long compared to the time that the molecules stick for. What you see then is that the loss is, over time is reduced, and it's consistent with there being essentially no loss in the dark. So that sounds really good, because then you just build a dark trap somehow. But it turns out for other molecules, the same effect is not observed. So this is actually, like I said, not completely understood. But it's important because, again, that creates these losses that has prevented us from creating quantum gases of molecules. And so maybe like yesterday we said something like our frontier is, many body stuff solving large systems, but this is not the only thing. There are also, this is just two molecules, and we've basically no clue what causes loss of these. Okay. So then, but then in this talk, I basically want to talk about something more positive, is that we can still prevent these losses by what we call shielding. So the idea is, again, you have normally some long-range attractive von der Waals interaction, and then the molecules come close together and they're lost. We don't know why, but we can still prevent it by somehow engineering repulsive interactions to just keep the molecules apart. And there are actually many ways you can do this. I think the most intuitive thing is to confine molecules to 2D, just polarize them perpendicular to this, and then I'll have repulsive dipole-dipole interactions. But that'll work in 2D only. If you want to do it in 3D, there are some other options. You can apply electric fields of a particular strength that causes some Förster resonance, which will also create repulsive interactions, but now in 3D. And there are many other proposals. So there are proposals using optical transitions, Raman transitions. There's even something using parity doublets in polyatomic molecules. And what I'd like to talk about here is this idea of microwave shielding. So it's, again, shielding, but now it's the microwaves that somehow create repulsive interactions. So this is just to illustrate, this is a bit of a cartoon, but where it comes from is if you have two ground state molecules, they have this attractive potential that we don't like, but then we can dress them with microwaves on a rotational transition. So you excite one of the molecules, absorb a photon. If you're blue attuned, the quasi-energy, let's say, is just below your initial state. But now you have a ground state and an excited state molecule, so you get resonant dipole-dipole, and you get this repulsive potential that crosses the ground state. So now all you do is you increase the Rabi frequency to make that crossing avoided, and then hopefully the molecules will just follow this upper potential and they're shielded. Of course, they might not do that. They might make a non-adiabatic transition. They can be lost here, or they can even dissociate down here, which is also a loss mechanism. So this is just a cartoon, and this is actually analogous to blue shielding for ultracold atoms, which never really worked because of spontaneous emission. But with these rotational transitions, we don't need to worry about this. They basically live forever. Okay, so then another comment I heard yesterday is that we're losing knowledge of how to do coupled channels scattering calculations. So we study this by coupled channel scattering calculations. So this is a proposal together with Jeremy Hudson where we calculate loss due to these two loss mechanisms as a function of Rabi frequency and detuning of the microwave. So we're basically looking for parameters where you can suppress both. And it turns out you can realistically suppress losses to something like, okay, there's a number 10 to the minus 14 cc per second. This is basically buys you, tens of seconds of lifetime at a density high enough for a BEC. And you can do it with high but reasonable Rabi frequencies, almost resonant dressing, and circularly polarized microwaves. If you do the same thing with linear polarization, it just doesn't work. So then, maybe to comment on the role of theory here, in principle, building this should not be that much more difficult. I mean, maybe the experimentalists on YouTube should cover their ears. But in principle, what I'm saying is build an ultracold molecules experiment, which is terribly complicated. But then on top of this, you add just microwaves, which is very accessible technology, and you should be able to shield them. When I proposed this, everyone was really scared because, okay, I mean, for linear polarization, it doesn't work at all. So how close to circular do I need to be? And so maybe the role of theory is also to figure this out quantitatively and guide experiments towards this. Yes, please.
A very basic question
Yeah.
about the color scale. When I'm looking at this and you're saying that the linear is not working,
Yeah.
but there is a big purple reason.
Yeah, but then you have, this is just, large detuning, small Rabi frequency. This is basically where you're not dressing. So then you have the normal losses by the molecules coming close together. Yeah.
So you rule that out for this.
Yeah. No, this is all red. This is not
so
good.
Basically, always that
Yeah.
one plus that one.
Yeah, I want both loss mechanisms to be absent.
One is not good.
Yeah. Yeah, thanks. Okay, so then we figured this out, like what happens if we actually put not perfectly circular but elliptically polarized microwaves. And so this polarization is characterized by this angle psi. And so you see that if you're circular, that's here on the left, you get a very low loss, but then it increases very rapidly. There's not like a phase transition here, but if this ellipticity is larger than a few degrees, the loss really goes up orders of magnitude. But maybe you should be able to build this thing. And then there are other sort of idealizations that other effects that could play a role. For example, we're playing with rotational excitations, and the hyperfine structure is completely different in every rotational state. So basically, you couple to many, many hyperfine states in the excited state, and you could worry that all these avoided crossings lead to additional losses. So we look at the effect of nuclear spin also in this. And so indeed, you see that in principle, it can enhance losses by orders of magnitude, but it can be suppressed by a magnetic field, which happens to be at only about 100 Gauss or so. So this is experimentally accessible in essentially all experiments. So yeah, again, the role of theory in this, I guess, is to really guide experimental realization of this microwave scheme. And so it was first realized close to here in the group of John Doyle at Harvard. And so we're doing the shielding. Okay, this is actually not the shielding yet. This was a previous study they did. They have laser-cooled calcium fluoride molecules in optical tweezers. So they contain a single molecule, and they use this to measure collisions by merging two tweezers that each contain a single molecule. They hold them for a little bit, wait for collision, separate, and see if the molecules survive. So the idea was just to repeat this, but now dressing the molecules with microwaves from this antenna, which, okay, is not just one antenna, it's just to make the polarization clean. So the idea is you can prepare molecules in a state with a repulsive potential to get shielding. Just as a consistency check, you can do the reverse and create a attractive potential to speed up collisional loss and do a kind of anti-shielding. So you're looking at the survival of molecules over time. This is without microwaves. And then you add the microwaves first in this anti-shielded state. Sure, you can increase additional losses. The lifetime goes down by a factor of 5 or so. And you can also try and prepare the molecules up here, and then the lifetime's extended by a factor of 5 or so. So this was for me it was a very cool process to collaborate on this and to see that it actually works, not yet by the orders of magnitude I just promised, but still is a promising first factor of 5. So there's a lot of sort of technical reasons why with these molecules in intense tweezers at relatively high temperatures of tens of microkelvin, the shielding would, or think even 100, would be less good than I just promised. And it turns out all of this would work better in a gas of ultracold bialkali molecules in optical dipole traps. So I collaborated with such an experiment. This is in the group of Emmanuel Bloch and Xinyu Luo at MPQ. They have fermionic sodium-potassium molecules, not in tweezers, but in an optical dipole trap. Sorry, I should have probably mentioned here also on this experiment, I started talking about evaporating to a BEC. Obviously, with 2 molecules in a tweezer, we can also not do this. Okay, so let's try this for bialkali molecules. The same thing, dress them with microwaves from this antenna. And then we're looking at collisional losses and elastic collisions. So this is as a function of detuning of the microwaves from the rotational resonance. We're looking at collisional rates. So you can see that if we go close to the resonance, we can suppress collision losses, again, by a factor of few, a small order of magnitude. But we also get a huge increase in the elastic collision rate by orders of magnitude. You can even see that, okay, so there's measurements here and calculations. This is my solid line. So this agrees pretty well, except maybe here, where elastic collisions in the calculation are even quite a bit faster than is seen in the experiment. So this is because in the experiment, elastic collisions are measured by thermalization, and this is actually at some point capped by the trap frequency. This is the hydrodynamic regime, where basically collisions are no longer what limits the thermalization. It's just a sloshing in a trap. So basically, this means that, okay, I started talking about molecules which collide and have collisional losses and no elastic collision, so you can't evaporate. But now we're actually, somehow this shielding is so effective, we're in a completely opposite regime, where now even elastic collisions are not just dominant by a small factor, but they're even so large that you can no longer measure the cross-section. Okay. But of course, it's not so bad. You can still use this for efficient evaporation. So we start here, this plot runs, this is molecule number over evaporation ramp, so it runs right to left. We start basically with a thermal gas, T over Tf is about 1, and then you can evaporate to a quantum degenerate, so a degenerate Fermi gas with T over Tf is about 0.4.
Actually,
Yes.
Really stupid question.
Yes.
I'm sorry. So, if you, and this you show this here, I mean, if you try to evaporate, you want elastic collisions.
That's right.
So, at what point do elastic collisions get so bad that you say, oh, no, we don't want them anymore?
Oh, no, I want them, but I mean,
But you kind of showed that as something negative before because they are.
This bit, I mean, what's negative is that this hydrodynamic regime is sort of limiting the thermalization. So at this point, we're no longer making full use of the fact that the elastic collisions are another factor of 5 or so faster.
But in principle, this kind of all the way to the left. Or where
this one needs to be behind us
is
a lot.
minimum,
yeah.
That's what you want.
Yeah,
Like,
it's basically the ratio, which is about 1,000 or so here. So, I mean, there's no real hard cutoff, but normally, you'd say where the ratio is about 100 or so, maybe evaporation can be efficient enough. But higher is better. That's, yeah. Okay, cool. Yeah, so, okay, so then we can ask, okay, but what is actually doing this huge elastic collision, right? So it turns out this is dipolar collisions. If I plot this not as a function of the detuning, but rather as a function of the effective dipole moment, which is just set by the microwave, sorry, you cannot see this. It's set by the ratio of detuning to Rabi frequency. You see we get a very nice dipole to the 4th scaling. This is just dipolar collisions that we're looking at. This also gives some ideas of how you could control this because basically now we can control the dipole moment induced by the microwaves, again by playing with the detuning, but you can do more. You can also play with the polarization of the microwaves. So this is looking at the potential now in the plane of the microwaves. It's isotropic and attractive. When the polarization is circular. But we can also make it elliptical, so you change even the anisotropy of the interaction. And now in this same plane, it's now repulsive in one direction and more strongly attractive in another. And the nice thing is that this potential really deepens, and so it starts to develop a bound state. And then if you go further, you can even have a second bound state. So we're sacrificing a bit how well the shielding works by going to elliptically polarized microwaves, but you get basically states that give you resonances and can control collisions. So we're looking at this here for these three polarizations. So the green one is basically circular. So when you detune, the shielding becomes less good, but there's no special features here. Blue, the ellipticity is larger, so that at resonance there's actually a bound state. And then what you're doing is you detune, so you push that bound state into the potential well becomes less deep because the dipolar interaction becomes weaker. You push that bound state into the continuum and you get a resonance. Yes?
What takes there or varying the theoretical condition?
I
guess that the shade that is theoretical.
Oh, okay, thank you. Yeah, it's not really an error in the theory, but rather, so in the experiment, the ellipticity was, I think it's the ellipticity was uncertain. So it's done for basically what we think it might be. Yeah, and then if you want to be really nice and ask, why is this mismatch? I mean, I chased this for months, and it turns out that it wasn't me. It's actually that the microwave power is not in the experiment is not constant on this axis, which experiment's always supposed to be right. But, okay, sorry. There are no experiments. They're not listening. Okay, so then the next question is, okay, how do I get to a BEC from this? Because, okay, sounds very nice, but so far you've promised orders of magnitude of reduction in losses, and we've seen a factor of 5 reduction in 2 experiments, right? So for the fermions, that's nice because of the p-wave barrier, you start with a very low loss rate, you boost the collision cross-section by orders of magnitude because it's dipolar. So in this case, it buys me a nice ratio, but for bosons, you don't have that p-wave protection, and you're starting off with losses that are orders of magnitude higher. You really need to reduce them by, I don't know, at least 2 orders of magnitude. So I started collaborating with, what's the volume? I started collaborating with the group of Sebastian Will at Columbia University. It's basically the same idea. We have experiment molecules, in this case it's sodium cesium, in an optical dipole trap, microwaves from an antenna to create a repulsive potential and protect them. Okay, so this is on the left, the main result on the shielding is a similar plot to just now. The loss rate as a function of detuning. You can see that we can really suppress losses by about 2 orders of magnitude or so. And on the right, well, okay, and so this really increases their lifetime by about 2 orders of magnitude. You can try and evaporate. So this is, again, a similar plot to before, but now looking not at temperature, but at phase space density. So this I want to be high. Around 1, you get to transition to a BEC. So we're evaporating, reducing the molecule number, but at least the phase space density is steadily increasing until, unfortunately, it levels off at about 0.1, and we don't quite reach a BEC. So what we thought is happening here is, back to this plot, okay, this looks very nice here. We're suppressing collisional loss, both in the experiment and in the calculation. And then when you go really close to resonance, my calculations suggest that you're suppressing collisional loss better and better, but in reality, in the experiment, you see that there's some sort of additional loss that kicks in. And so the hypothesis is, okay, the calculation is 2-body, maybe this is 3-body loss. This is kind of, well, there's stronger proof than this, but something else that backs this up a little bit is that, if we look at different temperatures, then over here, in experiment and calculation, you have a very weak temperature dependence, and the additional loss behaves very differently. So what we want to do about this is, So where it comes from is, okay, what we're doing is we're dressing with circularly polarized microwaves. This creates a nice repulsive potential, which we want, but again, outside that you have the same dipole-dipole interactions as before. And that creates a very long range, so this is at like 2,000 Bohr radii or so. It creates a very shallow long-range potential well that can nevertheless support a bound state. And so once it has a bound state, you can get three-body recombination into that bound state. So the hypothesis is that's causing this, and that limits the evaporation at some point. So what we want to do is add a second microwave field to basically cancel that dipole-dipole interaction so that the potential is completely repulsive. There's actually a proposal that basically does this using microwaves and a static electric field, and this is basically the full microwave equivalent of that. Yeah, so this is just sort of illustrate what I mean by this cancellation of dipole-dipole interaction is maybe a bit excessive, but the idea is, okay, we're putting molecules in an oscillating electric field, so the molecule will have a dipole moment that starts oscillating. On time average, it's 0, but you still get dipole-dipole interactions. If I take two of these dipoles like this, then at every point in time, their dipoles are pointing in the same direction, so the interaction is it doesn't average to 0. It's always attractive if they're head to tail like this. It's actually anisotropic. If they're not head to tail, it can also be repulsive. It's just this normal dipole-dipole interaction. And the strength of the effective dipole moments, again, controlled by the Rabi frequency and the tuning of the field. With circular polarization, you kind of have the same. You now get a rotating dipole moment. And again, when you take two of them, the interaction doesn't average out. So if they're rotating like this, they're always head to tail. You, for the same approach of the molecules, you now get a repulsive rather than attractive interaction. So actually you have, again, dipole-dipole, but now with reversed sign and the dipole moment controlled by a separate field. So if you control both, you should be able to take the two, add them, and cancel the dipole-dipole interaction. So this is showing what that does to the potentials. So in orange is the one using a single microwave field where you get the potential well that can support a bound state. When I put a second field with this particular detuning, then I can completely cancel this dipole-dipole interaction. It's a great potential here. It's completely repulsive. And when you detune a little bit, the cancellation is not 100%, but still the potential well, so you get a bit of a dipole moment, but the potential well is much shallower than it was, and it can still have zero bound states, and so no three-body recombination. So this is showing basically a dependence on parameters here. This green region, this is shown as a function of detuning of the two fields, shows a region with 0 bound state. So this is where we can presumably work without three-body loss. And so it's not narrow, it's many megahertz wide, so it doesn't require complete cancellation, and we can still work with a bit of a dipole. Okay, so then the question is, okay, does shielding require the circular polarization, circularly polarized microwave field? I add a second field, can it still work? And so this is looking at the two-body loss as a function of detuning of one of the two microwave fields. This is the single field case in orange, and you can see that this double shielding, which is how we're calling this now, can actually have lower two-body loss rates at this compensation point where we want to work. So this is not the reason that we started doing this, but it's still nice. The real reason we started doing this is three-body recombination. And so this is looking at experimental rates for three-body loss as a function of now Rabi frequency of one of the two fields. This is the compensation point where we should have no bound states, and so no three-body recombination. And you can see that, okay, it seems to, at least we get a very low, I mean, it's basically an upper bound to the three-body loss rate here. It's very low. It continues to be low when you detune until you hit one of these dashed lines, which is where in the calculation the first bound state appears. So it really seems to be described by three-body recombination. Yes?
Matter of terminology, has this anything to do with the PIMO state, or it is not?
No, because this is a genuine two-body bound state.
Right, so but you say that when there are no two-body bound states, you still see three-body recombinations when thrown out there. But you don't have two-body bound states, but you do have three-body recombination.
You kind of, per definition, don't have three-body recombination. It doesn't, right? Because three-body recombination is you have a three-body collision where the product is, two molecules go into the bound state. That you cannot have. It doesn't completely tell you that there will be zero three-body losses, right?
Ah, okay.
Just like, yeah.
I should probably know this, but you should also be able to check just with like scale and density or something, whether this is three-body. Or just the shape of the loss curves.
Yeah, in principle, yeah, but it's difficult to really do.
It's not enough dynamic range. But
Yeah, I mean, the upper bound here is also set by just the inability to tell this apart from one body loss.
I mean, at least out on the wings where you do have the bound states.
This
You
bit?
can- Yeah.
Yeah, so here you get losses that you can actually measure, and you can describe them by dipolar three-body recombination.
So like the time dependence, the density dependence, and everything.
Yeah.
It's like three.
Yeah, okay, cool. Yeah, so then you can go back to evaporation. You can already see that, okay, so the red is with our new double shielding. We get a very good evaporation. It's better than before, and now it doesn't stop, right? We hit, with some molecules to spare, you hit the transition, basically unit phase space density, you hit the transition to a BEC, and suggestively you already see a condensate fraction growing. You see this basically by looking at the density before where the phase transition should occur. The density is just a Gaussian, it's a thermal gas in a harmonic trap. And then after the phase transition, you get, the wings are Gaussian, but there's a sharply peaked condensate on top of this that continues to grow. So yeah, we have a BEC. Actually, you don't really know from this per se whether it's a BEC or a droplet. So we can basically see this in time of flight expansion. And so this is shown here for the sort of aspect ratio inversion. So we're basically squeezing the BEC in the y direction, which increases if it's a BEC and it's a single wave function that increases the momentum in this direction, and so you see that before the phase transition, the gas doesn't care about this anisotropic confinement. The expansion is the same in both directions, and after you hit the phase transition, it starts expanding faster in the direction you've confined more. So we have a first BEC of polar molecules. It's actually long-lived. The lifetime of the BEC here was 2 seconds, which is actually not even limited by any loss, but by free evaporation. If you get rid of this, it's basically limited by the one-body lifetime of something like 10 seconds or so. We didn't even see losses in the BEC. And then, just to look forward a bit, we don't have not just suppressed collisional losses, but by the shielding, we can actually control interactions. Again, we've seen this before for dipolar interactions. But now, with this double shielding, we can control both dipolar interactions and the scattering length. So this is illustrated here. So this is showing both of these length scales that characterize these interactions as a function of detuning of one of the fields. Again, here's the compensation point. So the dipolar interaction is 0 there. And we've created a completely repulsive potential, which guarantees that the scattering length is also positive, which is nice to create a stable BEC. And then when you detune from this, the dipolar interaction grows. And at some point you hit these vertical dashed lines where you create a bound state. So we basically want to operate in between where the system is stable. But where you do create the bound state, you also have a resonance. So that means that the scattering length goes from large negative to large positive values, meaning, from this positive value here, we must go to large negative. We must cross zero. So we can basically completely tune interactions. You can create either sign of both interactions. You can tune either one to zero to make the other dominant. So this is basically, I guess, sort of the double meaning to this double shielding. We're using double the microwave fields to control double the loss processes, and you get sort of double control of these interactions. Yes, I'm almost done. I mean, just to say that just a sort of outlook for the future is that with this shielding, you can now make quantum gases of polar molecules and simultaneously control interactions. So this is basically what you need to use these systems to study quantum many-body physics. So you can think of sort of doing things that you can also do with magnetic atoms, but now with dipole interactions that are many orders of magnitude stronger. So there are some predictions of many new phases you can realize that you cannot practically do with magnetic atoms. Or you can think of maybe doing things in lattices even where it's not so obvious maybe that you would care about collisions when you look at this picture, but actually you want to load this lattice, and so doing this in a Mott insulator using a quantum gas, this is basically how you would do it. And so suddenly all of these things, these references are not very recent, but this is now all coming sort of within reach. So this hopefully a picture for a nearer future. Okay, so just as a conclusion, I've shown you that this microwave shielding can simultaneously suppress 2-body loss, 3-body loss, and control interactions, and that has led to the realization of quantum degenerate gases, both Fermi and Fermi degenerate gas and the BEC. So there's a growing list of collaborators to thank here. I've kind of highlighted these collaborations. And finally, just to mention that actually it's a very exciting time for ultracold molecules, and if you're interested in this, there will be next summer Aspen Summer Program organized together with Tim Lange, Sebastian Will, and Tanja Zelewinski, so look out for an announcement. Thank you very much.
Thanks. We have time for questions.
You gave a very compelling explanation of why the second shielding works to prevent free body recombination. Any idea why the double shielding actually improves the shielding itself, the basic was, you didn't really explain.
Yeah, I didn't really explain. I don't know if I have a very intuitive answer to this. It's actually, I mean, in general, it's relatively difficult to, if you, let's say, you look at some potentials to explain how good the shielding works, because, in the end, you create a repulsive potential, fine, and then what creates the loss is just non-adiabatic transitions. Even though there's no crossing, and even if there were, you're not really making a completed crossing. So there's no very simple model to explain this very well. So
it's sheer luck that for that the potential just happened to be cross in the right place.
Yeah, I mean, I can. I'm sorry, I can show you, it's not in this presentation. I mean, I can show you potentials. They end up actually, you can make them quite, I mean, by eye they look similar to the sigma plus only and very different from the linear polarization. Again, with the ability to tune the dipole-dipole interaction. I don't have a very intuitive explanation.
Luke.
Yes, so you probably said it and I lost the thread of it. So these are 3D Bose-Einstein constants, right?
Yes.
All right, so, but at the beginning you said it would be easier to enforce repulsion if we were confined in the molecule in 2D. So are there, because you can align the thing, cool them down, they're fed, so are there evidence of DEC of 2D assembles of atoms, of molecules, polar molecules?
I mean, what I said is that it's easier to understand, I think, how you create the repulsive interactions. But I mean, if you just go, I'm sorry, it was, where was it? Yeah, I mean, this has actually been done in Junyi's group at Gila, the
Alright.
evaporation.
And so they do have this layer of BEC.
Yeah.
I see, okay, there's just the only
It's
thing.
fermions.
Oh, yeah. I mean, there's no other BEC. I'm sorry, no. These are fermions. But you can use this to. Sorry, this is what I meant. I guess you can use this to suppress collisional loss. It's probably actually easier to make the fermions 2D rather than bosons. But I mean, sufficiently 2D for this to work. Yeah, but again, if you want to.
Just because the argument that I heard was, okay, in 2D it is easy to make the repair, but we want to do it in 3D, so I wonder, did they do it in 2D?
Yeah, this has been done, but again, maybe you want
But
to
it
do
is not
something
a
in a
BEC.
3D.
But it's not a BEC.
No, again, they're fermions, so they cannot make a BEC.
It's not really that much easier to do 2D. I don't know, but it's just my...
I thought my statement is easier to understand.
I
You
see.
create repulsive interactions than for this microwave dressing. Yeah.
Well, thanks for
Okay. Yeah.
Kaden, do you have a question?
Yeah.
Yeah.
So since we've waited 20 years for BECs, let's try to project shielding 20 years into the future. I guess I'm curious how much you might be able to improve this. So for example, by additionally dressing with other rotational states or something, you might be able to craft this potential and get loss rates even smaller. Do you think that's possible, or is this more or less as good as it gets?
I mean, even without adding really new things, in principle, this shielding could be much, much better using higher Rabi frequencies, which are, I mean, in the end, the shielding with for sodium cesium is done with Rabi frequencies of, I think, something like 4 megahertz, and they can do like 60 or so. The thing is that they don't, then somehow I don't know, they have some filters to reduce noise on the microwaves, which in the scheme give you a kind of one-body loss. And those work better here, so it's kind of a trade-off. But this is completely technical, right? So it's
Okay, so you're not running into other hyperfine states or something, it's just a microwave power issue.
Yeah, I mean, I'm not saying there are no, you're asking for a smart new scheme that will do better, but I think, which may also be possible, but even just technical developments could. Yeah.
Jessica.
Maybe just projecting forward, just to understand, one of the difficulties about molecules, because they have so much more degrees of freedom, you need to do additional shielding and kind of additional tricks to kind of prevent losses. How do you see, as molecules get more complicated and people now start to cool polyatomic molecules, do you see a path of these shielding schemes to kind of get us there, or do you think that new ideas are also important? Very open-ended question, sorry.
Yeah, no, it's good. No, but I mean, you're right. I mean, people are seriously laser cooling polyatomic molecules. There are even, I mean, there's even, I don't know if this is going to work, but there's even a pathway that people are considering using the shielding to make polyatomic molecules, because again, you're making, I mean, you have these field-linked states, right? So you can make a bound state of let's say 4 atoms with, in 2 molecules that are admittedly 1,000 Bohr apart. So, getting them into an actual tetraatomic molecule is still difficult. So that's one thing. And then, yeah, like you said, there's the cooling where at some point you're you have to switch from laser cooling to collisional cooling, right? And then you would need this, presumably. Yeah. I think there's also, I don't know, there's maybe still the hope that if you actually understand what causes collisional losses, then you could just, like I mentioned, this the optical excitation, if you would understand different loss processes and you're somehow able to control all of them, then you might be able to do evaporation and things like this without the shielding. But for now, this seems like a more productive way forward, I think.
Okay, well, I think the future for AMO theory is coffee, and then more fantastic talks. But let's thank our two speakers again. And